Hello everyone. In this video we're going to go over graphing special functions. So in this case we're told to graph g of x, which we can see is a transformation of f of x given this rule right here. So first step might be to actually write the function rule for g of x, which is going to be this. Radical x plus 3 as a quantity, all underneath the radical. Sometimes I put a little ledge there not to confuse it, and then plus 4 outside. So this is what we're actually asked to graph, and obviously as we can see on the bottom there we have some follow-up questions. We're going to describe what this transformation looks like, and then the domain and range of our graph. We'll save that until we actually complete the visual graph. This way we can see things a little bit more clearly. So first of all here, remember why square root graphs are classified as a special graph. They're unique in the sense that they only have an endpoint on one side and an arrow on the other. So this would be your parent function. Very rough sketch. Looks something like that. Remember, radicals are not defined across all real numbers, namely square roots aren't defined, I should say, because we can't take the square root of a negative. So we have an endpoint, a cap, if you will, where on a calculator we see an error because we're getting that negative underneath. So we have an endpoint, and obviously it's continuing, usually to the right towards positive infinity in the other direction. Now graphing this, we are going to use a table of values, but let's first look at the transformation here. So there's really two transformations taking place. This plus 3 is obviously different. That's not featured in the parent function up here. And then the plus 4 outside the radical. So inside the radical we use what I like to call our IHOP rule. This is going to move it horizontal. It's inside the radical, or underneath the radical. And it's an opposite movement. What do I mean by opposite? Plus 3, if you think about a number line, you would usually say 3 to the right. In this case, we're going to say 3 units left. The plus 4, anything outside of a rule for any graph, absolute value, quadratics, anything outside of the rule that where you're just tacking on or taking away is going to move that function up or down. In this case, it's going to be up 4 units. So we have our two transformation rules. In terms of things in front, obviously we don't have anything here, but if there's any type of negative sign, that would reflect the graph over the x-axis. Anything with an absolute value larger than 1 is going to be what we call a vertical stretch. Anything with an absolute value between 0 and 1, we're going to call a vertical compression. We don't want to use words like skinny and fat and things like that. We want to make sure we use correct terminology. Even with what we have here, I should really use words like horizontal, 3 units. We want to be as formal as possible. All right, now actually graphing this. I'm running out of space here. I'm just going to erase this. I'm going to make a little table of values. So this is where actually writing the rule, the first thing we did, is going to be useful because we're going to type this into our graphing calculator. Square roots can usually be done with, I would say, 3 or 4 points. And the trick is picking nice points. Obviously, if you take a square root of a perfect square, you get an integer solution, an integer output. So those are the values that we want to include, not the crazy decimals in between. And obviously you want that endpoint. You don't want to just be starting anywhere in the graph. So I'm going to start where the radical, the radicand, is 0, and that's at negative 3, 4. That's the smallest value I could have in the radical because it is creating a 0. And then I'm going to pick a few more nice points, negative 2, 5, 1, 6, and 6, 7. Okay, I'm going to carefully plot these. 1, 2, 3, 1, 2, 3, 4. Negative 2, 5, 1, 6, and 6, 7. 1. And now once I have them all plotted, I'm going to draw as nicely as I can. A little bit of a curve to it. I don't want to make it look too linear passing through those points. Notice how I do have an endpoint. I do have an arrow. Obviously I can take the square root of larger and larger integer values, but I can't take anything over here, which is why I have an endpoint. That's the lowest value I could have. All right, and now let's finally answer that bottom question. What's the domain and range of this graph? When we look at the domain, we're really asking ourselves, what x values are allowed in this graph? Whereas with range, we're looking at what y values are featured, what y values are possible, what outputs can you get for this function. So let's start with domain. If we're looking at x values, we're really looking left and right. Okay, so obviously we have a further left endpoint here. The smallest x value we can have in this graph is going to be that -3. And it's going to go all the way to infinity. There's no endpoint on the right in terms of x, so I put like a little dotted line. That goes on forever. Now notice -3 is included. I have a filled in circle here. I can actually plug in a -3. If it was an open circle or a function maybe where -3 is not defined, I would want to choose a different symbol there. Now another way to write this is probably more common. Interval notation. The brackets indicate that's included. The parentheses indicate we can't equal infinity. Now for range, we're looking vertically. Those are our y values. What y values are possible? We see that there's a smallest y value, and obviously, although it's growing very slowly, this is going to keep getting larger and larger as x increases. That's going to go towards infinity. So we call this g of x. You could use y there as well. It's going to grow to infinity. It does have a minimum value here of 4. The smallest output you can get in this graph, and you can actually attain that 4, so it's equal to 4. And in interval notation, 4 to infinity. That's my domain and range. So this is just a quick recap on how to graph special functions, namely square root functions, by identifying transformations using a table of values and then analyzing the domain and range. Be careful with coefficients in front. Once again, I'll do a quick, I think I said it verbally but didn't write it down. If we have something like, let's make up two new functions. 2 radical x versus 1/4 radical x. And this is really what I meant earlier. You can get away with saying things like wider and narrower with quadratics and with absolute value, because we could literally see, that U shape may be getting a little bit wider or getting a little bit more narrow. It doesn't really make sense here if we try to use the word wider or narrower. So we want to use things like, obviously 2. If we think about quadratics, that would make a little bit of a more narrow or skinnier quadratic. But the formal definition here is that it's making it, we're doing what we call a vertical stretch. Whereas a fractional absolute value, anything between 0 and 1, not including those, is going to be a vertical compression. That's going to get closer to the x-axis, whereas a stretch makes it further away. Okay, so it's just an additional vocab for transformations. We want to make sure we're using this terminology and not narrower and wider. And that's everything now. Thanks for watching, and hopefully this helps with your special function needs. Thank you.